chip in a little bit with regards to the practical, actual, on-the-ground reality of what edge and dealing with edge feels like. Right? Hello everybody, welcome to the O4S podcast. I am here today with Arjun and Ruturaj. I'm Shasak, and today's topic is fault tolerance in specifically edge computing systems. We'll be covering some broad topics around this area, and I guess we can start. Maybe you guys can introduce yourselves once more for the audience.
I'm Arjun, I'm a lead engineer and a software enthusiast.
Because I'm Mark Edge, working in the engineering team.
And I'm Shasak, I'm also in the engineering team, and Ruturaj has been doing all this. He's one of the key engineers on the edge device side. That's why he's here with us today. Last time me and Arjun did a discussion on the edge ecosystem, and he couldn't be here, but this time he's here. So we will definitely chip in a little bit with regards to the practical, actual, on-the-ground reality of what edge and dealing with edge feels like. Right? Okay, cool. So we'll be covering fault tolerance today. So we have the first agenda of the meeting is to first of all understand what fault tolerance means, like technically where we stand when we say fault tolerance, and what is also something in auxiliary topic that always gets associated with fault tolerance, which is availability. So what is fault tolerance? What is availability? Arjun, maybe you can start.
Okay, so I think the definition that I stand by is that availability typically has 5 nines. That's 99.999% of the time it's available. Okay, the system is available. Fault tolerance is the ability for a system to resist any failure, which is pretty much tending to 100%. And it's usually harder, though they're two different things, it's harder to achieve fault tolerance, and fault tolerance also comes at a much greater cost because you are being preventive in failing. Whereas availability is you could have multiple systems that provide kind of backup and they are available for each other. I believe what we're trying to do is more availability than fault tolerance in a technical sense, but I'll let this definition, the other people can agree or disagree.
I think I agree on the availability can be handled by having more number of systems as well as, but individual systems fault tolerance is I believe are more than that, I believe, because it's harder to keep the separation between availability and fault tolerance, because the end result is obviously the same. I mean, the user is facing a particular downtime or the cost issues that come with it. But as an engineer, I believe it is very critical to keep the separation between availability and fault tolerance as a whole.
Okay, so I will also pitch in. So I come from the cloud side of things, so you guys are working more on the system side of things. So in the cloud world, the way we define fault tolerance is that any system, basically what a system is like a combination of components. So if I draw a black box like we used to do in physics, V-body diagrams, right? Like, okay, these are the parts of the system, everything else is not part of the system. So for this system, its individual components, if one of the components fails, the system should not fail. So fault tolerance would be that if a particular component fails or multiple components fail, the system is still operational, it's not completely failing, and that is the cloud side definition of fault tolerance. And availability is what we understand as the result of fault tolerance. Like if your system is able to stay available, so like a very simple formula that we use to give SLAs on availability is that if our system was on for X number of minutes in a month and it was down for X number of minutes in a month, then for Y number of minutes in a month, then it would be defined as X minus Y by X times 100. This is the availability formula. Like this is the amount of time your system was actually available. In order to achieve that, we have to build the system in such a way that there are enough components that if one component fails or a bunch of components fail, the system is still available. In order to achieve the thing that you were just mentioning, that 5 nines, 6 nines, whatever is your standard of availability. different systems offer different SLAs. So whatever is your SLA, in order to achieve that, to me on the cloud side, it's like fault tolerance is the first step towards achieving it. There's many other things that we need to do to ensure availability, but one of the things is fault tolerance. So this is what I understand by it.
I think I don't want to get stuck in the definition, but I think it's a good starting point. I think there are certain things that are contentious about these definitions, but I think overall we agree that there is a relationship between fault tolerance and availability. I think the only contentious parts which are a bit tricky is that how do you define a component also, right? Because and these things become important later, because when we say if a component fails but the entire system continues to function, for instance, a database is now, are we talking about a single database VM as a component, or are we talking about two databases that are clustered as a single component? So this is where I think certain things get lost in translation. But I think overall, it is. I think we can just use this as a kind of a starting point.
So I guess broadly speaking, we understand fault tolerance, we understand availability, we understand that they are related, obviously, and it's also important to highlight that since these are definitions, there are always edge cases, boundary conditions, like maybe your system has individual systems that independently are fault tolerant, and then you could calculate the fault tolerance and availability of your whole system that is comprised of other systems. So we can go to any level of
and this would have no end, and that's the reason why we're all being sensible and kind of agreeing. Otherwise this topic would not itself have a discussion end.
Absolutely. So I guess having established that, so right now I guess what I'll do is give a brief of what the edge is about, because now we are getting into the topic of how it is different because in the cloud, like, there's enough resources out there, people know a lot about how fault tolerance happens in the cloud. But what is interesting at O4S is that we're working on the edge computing side of things also, and over there we are now facing issues with regards to fault tolerance. So we want to dive deeper into that. In order to do that, I'll just give you a brief overview of what the product is supposed to be doing from an end user perspective. So essentially we have O4S basically helps digitize physical products, right? So if companies are manufacturing at their manufacturing plants, say for example a packet of Maggi or something, what O4S does is that every packet of Maggi gets a digital identity which is unique to that packet, and we integrate with hardware that is available on the plant to attach that identity to that packet in the form of a QR code, right? So that it is very easy to add information or track that particular product across the entire supply chain with whatever transactions that happen on that packet. So this is the goal of the MARK Edge device, which is to get into those plants and be present there, run offline, and be able to integrate with all these peripheral devices like printers, scanners that are running on the manufacturing lines to be able to deliver this end goal. So this is the overarching idea of what MARK Edge does. And now we can get into what is the specific challenge that we face with regards to availability and fault tolerance on MARK Edge. So I will give you guys.
Okay, I think probably a good place to start would be where Raj can tell us, based on his experience of fire issues, is that typically when we face a system like maybe the database getting corrupted on a single VM, what is the loss of production? Because you see all these things have a cost, and what is the cost to the client versus how much you have to invest to prevent that cost. So Rituraj, one question that I have for you is that typically if a database gets corrupted, right, from the point that issue is detected to recovery, what is the kind of time you're looking at without fault tolerance or automated recovery systems? What is the kind of time that goes?
I think this is where the cloud side and the edge side differs a bit, because cloud side we have the side is pure overly automated. You know everything that's get broken. It can be through event notification or everything. But on edge side we are relying mostly on plant operators to tell us that this system failed. And most of the time, because they are not looking or interacting directly with the system, it gets delayed a bit. And most the edge system is also structured in a way that it is difficult to understand whether it's a machine's fault or it's an application level fault. So typically it ranges from around 5 to 6 hours to around 1 or more than 1 day
to report the issue.
To report and to get into the court issue and maybe to propose a solution.
And so specifically, if you look at the most critical component is probably the database, right, which is most likely the faulty part. When we see database faulty means that there's a data corruption issues that happen for a lot of reasons, and that typically, I think, to restore the database takes what, 4 hours?
Restore obviously takes, the time is obviously dependent on the size of the database, and hopefully for it is still in recoverable state. It will still depend on various other factors like the system's processing capabilities and also the size of the database. But mostly it's the size that may actually depends.
So we're still talking about the order of hours at least, right? And because what I'm trying to do here is establish what is the cost, right, of kind of not having a fault tolerant system, right? Basically, that's the point here that I'm trying to make. So I think
4 hours might be a good time.
Right. So the thing is that, one of the things to kind of look into is that when you're looking at a fault tolerant system, you have to look at what are the components of your system that are critical and at the same time, most likely to go down, right? So you probably create a matrix saying, okay, this component will go down very often, but if it's not very important, then that's not something you want to focus on, right? And I think what we find is that typically we are not getting motherboard issues, and typically we have a backup system, but it's usually the database that goes down. And the problem with the database is, see, you can always swap in a new motherboard, you can always swap in new RAM. The switchover cost is very low. But with the database, the problem is that you have to restore the data, and that data is not necessarily backed up. We are, of course, now we can talk about when we talk about the initiatives that we're taking. We'll get into that, but right now I'm focusing on the problem statement, and that's like where the critical issue is. And to get around that's where the database is the first point that we're trying to make sure is available and is fault tolerant, right? How we're planning to do that, there are basically 2 strategies right now at the edge side that we're trying to look at. One is basically having a cluster database. Now again, cost is a factor. We can't have a cluster of more than 2 systems right now, but we're trying to create an automated setup of a cluster of 2 databases minimum, right? And then basically create on top of that a backup and recovery system, which is as frequent as possible, which backs up on that cluster. Now what's interesting is having a cluster makes the backup process faster and easy also, because if you have a single system, taking a backup on that single system is also resource intensive. That's another issue we have on the edge side, because your CPU, your RAM is limited. Now if it's very easy on the cloud side to say take regular backups, on the edge side a regular backup means stop the world process, right? That while you're taking a backup, you may be, and remember this is on the edge, where the idea of an edge system is we are running mission critical applications real time, which is, so you can't take a backup necessarily while the system is running, busy with the system. So that's another challenge that you probably don't face necessarily on the cloud, or you could increase the number of resources, but we can't do that on the edge. So we have to build smart systems which are able to kind of understand when the system is not in a mission critical state and backup. But having a cluster helps in that, because now you have a replica. The replica is not busy, it's the primary that's busy, right? But the replica can be used to take the backup. So in effect, having a cluster also makes the process of taking a backup easier, right?
And it's happening in smaller chunks, like every log entry is being backed up, rather than doing a bulk stop the world operation to do a backup and restore, that kind of thing. So that also sort of makes it so that it is interleaved between the operations of what's happening on the application itself, rather than, okay, for a while this is what the computer is going to do, and then it can go back to doing its job.
Yeah, well, if you are on the replica side, you could kind of take a full backup, and what we're also doing is mixing this up with the fact that we have cleaner scripts.
You mean the backup of the entire database? I meant like the replica itself is one backup.
Oh, okay, yeah. The replica is the oplog deltas, of course. Yeah, that's the definition of a replica. Yeah, I agree. But the backup. So what we're doing is we're also, in addition to the replica, we're making local backups, and we are uploading those backups to the cloud on an S3. So that way we have.
That's for recovery. Like if everything fails.
Everything fails, yeah. So if the replica fails also and the primary fails, then you can restore a system within minutes from like a copy, and that copy can be local or it could be from the cloud,
Yes.
right? So that's where we are heading towards right now.
Yeah, I think that is very nicely put. Like with regards to from the cloud perspective, if say for example we have to run a heavy operation or something like that, we can just spin up more resources temporarily, and then we can shut them down. And we do that on a regular basis on the cloud side. But on the edge side is that it's like, okay, even if you're creating a cluster, there are limits. Like I can't say that, okay, you take a 10, 20 machine cluster. We can't impose that on our clients, right? So we have limitations like, okay, we can at best do this much fault tolerance. Like, okay, maybe 3 nodes, maybe 2 nodes, but not more than that. So the fault tolerance number cannot just continue to keep going to an additional number of 9s. At some point we have to have restore capabilities, like because if there's just 2 systems, there's a likelihood that both will fail, right? In the cloud, if that happened, I would just say, okay, now we are going to have 3 systems, now we are going to have 5 systems, we want to make the availability 9.99, 9.999, so let's add more hardware, but we can't do that on the edge side. On the edge side, we have to have like, okay, both things can fail, individual components can fail, database can fail, so recovery options have to be there. We can't be in this state where like all the data is lost. Maybe slight amount of data will be lost, but like not all the data should be lost. So that is a backup strategy that you absolutely must have on the edge side, even if you have any kind of replication clustering going on, because there's a limit. So I think that's the key sort of key.
There's also some other key differences between the cloud and the edge. On the cloud, typically you have the luxury of having an independent arbiter or a load balancer that is determining whether a system is available or not. On the edge, we only have 2 systems, right? So that means the master or the arbiter has to sit on one of these 2 systems, and there is no load balancer, right? So that's another challenge that we have to deal with. Because if one system goes down, then who's there to assign the next system, or who's there to determine whether the system is available? So these are also challenges that we're dealing with. There was another point that was in my head, but I lost my chain of thought.
I mean, and there are other differences for sure.
Yeah.
With regards to monitoring and automatic feedback and all those kind of things. I think since on the cloud, like there are certain things that we always assume to be there, which would be, for example, if you are on AWS or GCP, I would be hard pressed to find an engineer who ever thinks that what if the network goes down?
Right.
Because that will almost never happen. It has never happened to me. I have never met a person who has ever said the AWS network goes down. Because over there they have like so many ways of recovering and fixing and repairing the networks in the data center in a controlled environment that you never face that issue. However, on the edge side, even the network can fail. Even the devices that are connected to you, the network LAN card that you're connected on to set up your makeshift cluster that you have put up together can fail. So let's talk a little bit about this aspect of fault tolerance also. Like you touched upon it briefly, that depending on the component we have to make trade-offs. Like we could say, okay, let's do a LAN switch array also and be like fault tolerant about that. But you mentioned like it's an easy to swap part, so we don't focus on it. So maybe the trade-offs are little. Maybe you can elaborate a little bit more on that.
Yeah, I mean, like I said earlier, that I think the trade-offs have to match that where is the maximum issues happening. Luckily, what we've been doing at O4S for the past, I would say 6-7 months has been measuring where the issues have been happening in terms of fault tolerance, and 99%, it has more than 99%, I'm just being conservative when I say that, it has been the database. We've never had like a CPU issue or a motherboard issue. Though we currently so from a component perspective, I don't want to just deviate from what Shasak is asking. I would still be very focused on the database, right? That has been the issue. And even in the database, it's not a disk issue typically, it's a database corruption issue, and I've not seen a bad sector till date, right? Though these are magnetic disks we are talking about, eventually they will develop bad sectors, but by then we have backup strategies, so that should be covered. But still, I think despite of all the challenges, we have not seen a bad sector or bad disks issues yet. Never a CPU issue, never a RAM issue, never a LAN issue. While in a theoretical fault tolerant sense, you literally, like you rightly said, ideally you should look at everything. But then again, practically as engineers, we have to look at what is the cost and what are the trade-offs. And the thing is that if the data has not suggested a problem in any of these areas and they're easy to swap, then we have to continue focusing on the database. So there is another issue that we have to talk about, is that typically in the cloud, what happens is that you look at your array of compute instances, right, like which is say EC2 instances separately and maybe your databases separately. So what you typically in an architecture, you don't look at like an architecture as a combination of a VM and a database. You look at as a clustered database as one setup, right, and then basically your multiple application pods which you typically want to be stateless, interacting with the databases or via like a Kafka or middleware, right, typically. On the edge that doesn't work. Reason being that when we're considering say two systems, right, let's just assume that there is a application software running on VM1. So this is VM1, this is VM2, right? And if an application is running on VM1, okay, and a database is running on VM1, if the database on VM1 goes down, though in theory you could have application connect to the database of VM2. You see what I'm saying? Because you got the database running both. But this doesn't work on the edge. The reason being is, this is not an available system anymore. Why? On the cloud it would be, right? But in the edge this is not. Because now what you have is, for my system to run, I need both VMs operational, right? Which is a problem, because I can't swap out. The ideal scenario is that I've got my primary, I got my secondary is an entire backup for my primary, right? So if my primary goes down, my secondary goes up, right? But if I have a situation where my primary is partially gone and my secondary is partially gone, now I have a system where there's like a crosstalk between these two systems, and that's not good, because now I need both to be available for my system to run, which is not an ideal case for edge. So what we're working on is that if the database of primary 1 goes down, then so the services go down and there's a complete switch over to secondary. Right? Typically in a cloud environment, you really don't care, right? Your application is logically a separate layer, even if they're the same physical machine, and your database is a separate layer, right? So that's another kind of important aspect to factor in terms of the recovery aspects. But again, I mean, I think I deviated slightly eventually anyway.
Yeah, it's interesting. Like, so what I understood from that is, like, for example, if I had to like set up a cluster. So what I would do is typically have like some sort of hypervisor layer on my operating system, and then on top of that my application would also be sort of replicated alongside my database. So if my node goes down or something goes down, this application that is running over here partially can still communicate with this other node. But the thing is that you have to make that investment, that okay, my cluster setup will have a hypervisor setup, you will have a load balancer, you would have an orchestrator. Only then this is possible.
Yeah.
Which is what we can't afford right now, because the resources are limited.
Yes.
It might require more hardware to set something up like that. And also engineering wise, like from the engineering team's perspective, it's like you need people who understand how to set up a hypervisor, OpenStack, how to deal with its particular issues and all those things. So you want to keep things simple also. You don't want it to be like there's like a whole data center sort of S problem statement in front of you now, rather than the problem that you're actually setting.
Yeah, I think the simple analogy is what, imagine if you had to create a data center of 2 laptops. It's not worth it, right?
It is a lot of effort to do that.
It's not worth the investment.
Yeah, maybe sometime in the future, not right now. So anyway, I guess this neatly sort of also goes into the point of, like, I think we covered this, which is the stateful versus stateless kind of thing. Like stateful systems, as you can tell, is much more, you require more consideration with regards to how you deal with fault tolerance and availability there. Stateless systems, you can just spawn them anywhere. As long as you're able to orchestrate that, you can spawn them anywhere. But with stateful systems, you have to keep in mind that you can't, even if all the components on your system are okay, and if just that component does not work, then maybe your system will just not be able to function anyway.
Right.
Either of those components mean nothing. And this is the same for the cloud also. The application layer is solid, but your database is completely, choked. Then what is the point of those applications running in the first place? So I guess with regards to fault tolerance, you can all agree the hard problem is in the stateful side of things, not in the stateless side.
Yeah, stateful side.
So you have been working on the edge ecosystem like quite extensively, and you must have faced like issues with regards to how to model the application in such a way that A, you are able to actually detect failures, like if there is a failure, we are able to somehow know that there is an actual failure, and we like reducing the probability of individual components failing. Like we talked about how a system has multiple components, and we're talking about fault tolerance and that. But there are aspects, I think Arjun, you can also change your perspective on this. That there are aspects of the software like, okay, how can a software be written in such a way that it actually caters to whatever the systems engineer is building in order to assist with fault tolerance and variability. So any light you would like to share?
I think application design also goes hand in hand, because there are also other factors like we don't consider, like the prime difference in data center, for example, data center and edge is that number one is the power, which is the source of everything. So like most of the time, if database is going down, it's mostly because power failure or those type of things. So because MongoDB in itself, MongoDB is a prime database that we use in edge. So that is pure. That has also individually built its fault tolerant mechanisms and all. So it's less likely that it will fail, but still it may fail. So but then our applications, if we design in such a way that the individual logics or the functionalities are more about segregated in such a way that, so then one issue that is happening in a particular part of software doesn't propagate to another part, which is I believe the prime part where we can detect a closed set of errors, because the difficulty in detecting errors is like there's a whole lot of things that can go wrong. So you need to reduce the set whichever way possible. So one big step will be to the design of the application itself, so that it doesn't let the errors propagate from one place to another. Because errors actually are defined by the context in which they occur. So once it propagates from one place to another, it may totally lose its context. So which means detecting and probably having at that point where it doesn't affect.
So like maybe, correct me if I'm wrong, but one maybe example of this would be like, say for example, a system design that is very tolerant to not causing the system to go into a bad state.
So I want to take a concrete example here. So I think abstract, and Rituraj makes a very strong and very valid point, and I just want to give an example here, actually, a concrete example. So one of the things that we're doing is that for instance, if the main process, right, which is written in Node.js, spawns some sort of script to clean the database. Okay, now the question is, if that main process goes down, does the cleaner process also go down, which is the database process? Ideally, no, right? Because if that cleaner process goes down, it can leave the database in inconsistent state. Now, it's very probable that the Node.js process that spawned that process could go down. So the way it's designed right now also, and this is what I think is a concrete example of what Rituraj is saying, is that if the main process was to go down, the child process will continue to function and complete its job. And because it's launched as an independent process, it's not, at an OS kernel level, it is a separate thread. It is not a application thread, which would imply that if the parent process went down, then the child thread would also die. So one of the design principles that we followed is that it spawns its own process, which does the database cleanup, so that even if the main process would die, the state of the child process is maintained and alive at the operating system level. So I think this is a concrete example of, I think, what
I think one more thing in this design, so like diving deeper into like software design itself. So one of the other things is like this management of shared state, right? Now, like you mentioned, we have multiple processes accessing the same state. So there are race conditions possible, like okay, what happens if I am trying to access a piece of data while the cleanup process is trying to clean up that data? What if the cleanup process has cleaned up the data which was not supposed to be cleaned up at that time because I was still accessing it? So designing your application states, like application logic, in such a way where they are able to isolate themselves becomes more critical because you have all these things. Like for example, in the cloud, I would never have to deal with these kind of issues, because if I am going to do an archival job or any kind of cleanup process, I can spawn off new resources. I can say, okay, just take a replica and do this on this replica, don't do it on this database or something like that. But here we don't have that privilege. We have to back up the database node itself. We have to archive the particular data on that. So over there now the application developer has to now keep in mind that the way I'm managing state, the queues that I'm setting up in my data, ensure that there is no possible way in which this kind of race condition can happen or something like that.
Yeah, I think that it always helps for the application developer to be aware and be sensitive to this. But I think, and there's also another topic I want to touch upon. It's called mechanical sympathy. Mechanical sympathy deals with the fact that, as typically in today's world, we have as developers have learned to think abstract. Mechanical sympathy actually reverses that. It actually makes you sensitive to the fact, and this is very relevant in edge computing. It makes you sensitive to the fact that for instance, each time I write to the database, as a logical thing, it doesn't matter whether I write 10,000 times a second or whether I write to a cache which is then finally persisted onto a database. But mechanical sympathy says, okay, let's reduce the number of writes to my database where we can group our writes together, right? That's one thing that we need to be aware of. Second thing, though, I see, but coming back to the point that you were making, while I think it is important for developers to be sensitive, at a system or an architecture level, I think the system has to be designed in a fashion where it is isolating the developer from having to make those decisions, because these are very complex things, and if the developer is not isolated from these problems, then you are going to have a very hard maintainable system. So on one hand, yes, I believe that the developer should know these things or should be sensitive, but we cannot rely on the developer only to kind of be doing this, because that would make for very unstable software. An example is what you were talking about. For instance, that if while the process is running, right, the application is trying to access the data, but the cleaner script is trying to clean the data. Now, frankly, the application developer is not aware of what other processes could be running, frankly. And I don't think the application developer should be aware also, because tomorrow I could be adding more scripts. So the context of that program should not be aware of what's happening. So what we've done is we have a system architecture in place where we have stop the world events. They are classified as stop the world events. This is what we are building right now. And if the container, right, that is executing these cleaner scripts. So firstly, we need to understand what is first citizen and second citizen, right? Again, contention. So if there's one thread, which is a functional thread, which is what we call serializer stop priority, because the factory cannot stop, right? Backup can wait, but factory cannot stop, right? So that thread is given priority, right? That process rather is given priority, and if that process is running, then the second process, right, which is likely to stop the world or requires a stop the world scenario, will not run. So firstly, you will not have two of these processes running together, and the application developer does not need to worry, because at the container level that we're creating, at the design level, it will not allow it to run. So that is what we are isolating and we're shielding such issues.
Doesn't it have like lots of unpredictability in your software itself, like with regards to why is my thread stalling, what is stopping this particular thing from?
No, it doesn't. So even if you look at the design of things like RTOS, real-time operating systems, right, you have to prioritize which thread cannot stop versus which thread can stop. When you do that, so the problem happens is in typical server programming, we don't, both threads can have access to a resource, and it's probably whoever gets the first access locks the resource, right, and requires a mutex on it. Whereas over here, you don't. You are very clear that these processes, the core functional processes, are given priority, and they will always run, right? So there are two scenarios. One is that my serializer is already running, in which case my backup will not run. Right? The second is my backup is running and suddenly the guy flips on the conveyor belt and wants to run the serializer, in which case it will hold the backup or pause it in a particular state and make sure that the prioritized thread runs first. So that it is always going to ensure that the mission critical application which is real-time requirement, will always run, and it will hold what is not mission critical. By doing that, following that strategy, you will never have a situation where your backup can fail, but that's okay, right?
I mean, I don't fully agree.
Okay.
But
Like to add something here, if you say okay, one can preempt the other, if it's one the backup creation script is running, and now serializer, the main service, needs to go on more priority than the cleaner script, or the cleaner script needs to host. So then I think this defeats the purpose of context isolation, in the sense that everyone, one or the other, needs to know that the other exists. If you say completely isolated,
So I didn't say that they don't know that they exist. What I said is the application developer doesn't need to know they exist. So the containers are aware of what can it execute, but the delegation of the responsibility of execution.
How will that person decide, the outside person, that which is the priority process?
Based on stop the world event. So it's pre-configured. So there are the stop the world event. So serializer, for instance, is stop the world.
So you were saying that there is a developer who knows about which processes require what priority. That developer is not the same developer who's building the process.
It's not a developer, it's a configured state, right? Like we know that this is a mission critical.
Whoever is the person who is designing the system that prioritizes.
Yeah, but it's a static one-time decision, which is much easier to handle rather than a dynamic decision where you're deciding which thread to get priority. So you already decided.
I'll give you a counter example.
Okay.
There's an engineer who creates a new process but does not tell this developer about this process's priority.
Right.
So then that bug can again happen, right? That race condition can still happen.
Yeah, but the thing is that the mission critical process that we have is only serializer. We only have so many. In theory, if you had serializer is the only. If you look at the software that we are running, right? If it is only there are two things: activation and serialization. Right? Activation is a scan event which doesn't require a very elaborate process to be running continuously. The only very resource intensive process that is running and needs to run for a long duration is the serialization event. And that is a one-time configuration. It's very rare that a new. If it comes up, it's an easier problem to solve. I'm not saying it's perfect. You're right. In theory, one can contest these things.
Without the knowledge of the application designer, I think it would be difficult to say with the fact that this will never happen, because they could be simply querying something and might not tell you about it. Like, I was writing this query on the database, but that query needs to run and make sure that it is running in isolation with the cleanup process. So if that developer just forgets, like, oh, I had this one query, they can introduce a bug. And the problem with these bugs is that these race condition bugs are very hard to track, like what happened exactly. And then they have to learn about, oh, there's a system level.
Yeah, I agree. I totally agree with that. I think the answers that you have to go via the container. You have to check that every developer who's developing this has to check with the container, is there a stop the world event? So there's a protocol basically, right? And that protocol is communicated. So rather than the developer having to worry about the intrinsics, so what I'm saying is that there's definitely some amount of awareness, but that awareness is abstracted to an abstraction layer or protocol. Right? And that's why we have protocols, right? So you have a protocol saying that the container will determine, right? You have to just watch out for stop the world events, right? And you inform the container whether you are a stop the world event or not. So that amount of education is, but beyond that, the container abstraction should take care of it. So that is where the trade-off happens. Again, it is.
I guess like you have to do both things in a way. Like the engineer who's writing the code has to make sure that he's able to somehow manage this state with regards to stop the world events. Like, okay, if there's a stop the world event going on, I cannot do this, or there needs to be and typically the programmer will not do it like that. Typically the way you would abstract that away would be with a resource lock.
Right.
If somebody has this resource lock, don't use it. And the other person who's acquiring that resource lock is the outside process.
Right.
So that the developer doesn't need to know per se. They just
Correct.
need to know about the resource.
Exactly. That's exactly the thing, right? You're worried about the lock rather than the process, individual process. So you're focused on a single, your attack area is very limited to just knowing about the resource lock or the stop the event world. That's what it's about basically.
So the architect of the software has to be like, okay, I'll give you these resource locks.
Yes.
And
exactly.
I have processes which can talk to the resource locks.
Exactly.
And then if you want to do anything in this, you have to acquire a lock, otherwise.
Exactly. So the application developer has to be aware of certain things, obviously, but then that limited. It's a standardized and it's limited to what they need to know. So it's manageable. Ultimately, it's about what's manageable. Otherwise, if each application developer had to worry about every process running there, that is unmanageable, right? So it's just about managing the problem. You cannot eliminate the problem.
Solve the
Exactly.
we're
not exactly. I think that's the point here that I was trying to make, was that we can't eliminate the problem, but we can manage the problem.
Yes. And I think that's a very good example, because this is typically the kind of thing that will only happen in an edge computing, embedded systems, IoT type of situation, where you have very limited resources. Because these days most web developers never really come across problems of this nature. That, there's this process that needs a lot of resources, which needs to run on this machine itself. There is no replica, there is nothing. I have to somehow manage this resource acquisition with this thing. So typically they are able to design systems that don't require locking. I mean, I'm a proponent of lock-free designs. So whenever I hear stop the world, log acquisition, I'm here on the back no, I need to design this in a different way. But obviously on the edge, you have to be practical. Like, okay, there might be a design that actually makes it log-free, but it is too expensive, or it's too resource intensive, and cannot be done on this machine. I cannot have a replica where you can do this. I cannot put this on a queue somewhere to do this in the background. So I have to find pragmatic ways of figuring this out in this small resource constrained environment.
And also
bring in a mediator sort of thing to handle all the resource allocation.
And also what's happening is that earlier on O4S focused a lot on the core functionalities that we built, like serialize, etc. Today we are focusing a lot on engineering stabilization. So these are toolings actually, right? And a lot of the software a lot of the code that runs is basically cleanup scripts, tooling and all, which is not mission critical. It is important to maintain the system but not mission critical. So we are making a separation between what's mission critical and what's not mission critical, and that's where the separation is coming.
Yeah, so the takeaway might be for people who have no experience in the edge ecosystem or are venturing in that ecosystem, is that you have to be aware of the fact that in a resource constrained environment, some of the goodnesses or nicenesses of the design might not apply. You'll have to find other ways of designing the system, so which is able to remain within the constraints of the resources that you have. And it is a two-way street. Like, system side also has to participate in understanding how the application is maybe scheduling things. The person who's writing the application needs to understand, okay, what resources do I need to acquire logs to and all that stuff. So they can't be totally separate 100%, but we do our best on the edge side. On the cloud, we can do total separation, absolute DevOps team has no idea what the application is doing. We do that, but over here, it's not exactly 100% possible, but we do our best.
I have an interesting problem for both of you actually, right? So it's like a trick, right? It's actually interesting for everyone. So earlier on, what we used to have is we used to have a single machine and we would have a backup. Okay. Now, the assumption is that the backup has been tested before. So if the single machine goes down, you have a backup to replace it. Now what we're doing is we're using the backup as a replica. That means it's live from day one. Okay. Now the problem is that if a backup is live, it is also being used and it is also facing physical wear and tear, right? Which makes the backup as equally likely to fail as the primary. So is this really a system that is fault tolerant? Because earlier on you had a system. If it fails, at least I have a backup. Okay, the only problem is that the state is not backed up. Now we're trading a real-time state replication, but for both physical systems facing wear and tear on all components, right? And here is the problem where on the surface of it, it may seem that this is a more available system, but the question is it really? Because now, you're getting what I'm saying? Yes. Both disks, there's no concept of primary or secondary. They're both machines, they're both running, they're both in the same environment, both facing the same physical shocks, same electrical failures. Isn't the probability of both failing at the same time in a given span going higher? And this is a question that I don't have an answer. In practice, I don't think it should be a problem, but in theory, this is something I'm concerned about. But we'll have to really try it out. I mean, I would like to see what your views are.
The way I see it, both really addresses different aspects or sides of the same problem. So the first one is, as you say, one system is readily available. It's not yet live, but it can come in live at any moment. We can replace it. And the second one is, of course, that the two systems are connected, they are replicated, the log entries are being transferred to the system. So the the state to both the machines are fairly at the same moment, at the same state. So I think the second one is more on the availability side. Although the two systems are going through the same stress, it's really unlikely. I am saying it's like not really, but theoretically it's obviously possible, but it's really unlikely that both the systems should go in at go down at the same time. But then again, these two systems being there live doesn't eradicate the need that there should be a third system which should be available for anyone to, if any of the system goes down, the third system should come in. So that the system kept as a backup, not being live, I think solves the issue when how much time does it need to solve the repair the database or take it back to the more consistent state. It might have some data loss, but you don't care because you restrict the loss to a minimum. But then when you try with the two systems being live and they are replicated, you are more concerned about the point-to-point changes or the database changes from one consistent state to another. You don't want that loss even. Like you don't want an hour of data loss. You want everything to be on at the same place, going at the same time. But then if both the systems goes out, obviously very rare scenario. But if both of them does go down, then obviously the first situation where we keep the backup system ready, that cannot be handled by this. So I like to think both of them as addressing separate things.
So I think what you and I think you're raising the right point, but I want to give Shastak also a chance to address this. But yeah, I'll come back to what you said, but I want Shastak to address this also.
So for me, it's like fairly mathematical. Like if, say for example, a system has in running condition a probability of failure, say x, right? And say the other system has a probability of failure 0. And combined, there still is a probability of failure of x, right? My system, if I'm assuming there's some ghost system waiting for me and it has like 0 probability of failure while it is in that state, then the probability is x. If I say both are live, then the probability, so if let's just say there was a 0.1 probability and that was like, okay, there's no chance that will fail, 0 probability. The total probability was somewhere like, okay, 0.1, because one system has to be run. Now if I bring both systems simultaneously failing, the probability is 0.01. So overall, mathematically, my probability of failure of the system is lower. And overall, arcingly, both systems simultaneously failing, the probability is now reduced than it was even before. And the final thing to this is that in this way, I can add more zeros. I can say, okay, now if I have one more machine on like that, the probability is now 0.01. I can expand on that. But if that system stays there, it will always remain that way. So to me, it is more mathematical.
Yeah, I don't think there's any answer. On the mathematical part, there is a slight contradiction in theory. And because maths is theory also, not just practical. According to the theory of probability, you have two kinds of events. One is independent events and one is mutually exclusive events. So mutually exclusive event basically means that two events are mutually exclusive if the probability of A is disjoint from probability of B. So that means P, A intersection B, right, is not equal to 0, right? Whereas independent events means that there is no relationship between the two machines. I think over here, frankly, in the theoretical sense, these are independent events because the failure of and this is where the trick is actually.
I'm assuming them to be independent.
Yeah, the trick is actually that if it's independent, then conditional probability doesn't apply.
No, but PA and PB apply.
Yeah, but PA and intersection B is equal to 0 because they are completely independent and there is no overlap between them.
So we don't care about intersection, we care about and here, right?
Right.
This and this both अगर fail.
Right.
So इसका probability of failure is something independent of this का. But together the systems both simultaneously failing is the multiplying factor.
Yeah. But then that's the thing also between theory and practice is that given the fact that both are experiencing physical, exactly the same physical stress, then Are they truly independent? So they're, so that's the thing. And that's why this is an open, innocent question.
Initially, it is very important. Like in physics, like we do, system boundaries.
Yeah.
Like if I'm studying thermodynamics, I'm like, okay, this is the room I'm studying right now. I'm not concerned with what's happening in the other room. So in that room, I make my definitions.
Yeah.
Same applies to sort of, in my mind at least, my opinion, is that you have to look at the system. Like my system is right now this one machine, because the other machine is not part of my system right now.
Right.
What is the probability of failure of my system right now?
Mm-hmm.
So that is 0.1. Okay. And if I had this other box also within this boundary with a 0.1%, 0.1 probability of failure, then now my system has a probability of failure of 0.01. So it's all about where you draw the boundary. If you include the other thing in your system at all times, then that is a different situation.
Yeah.
If you just operate on, okay, what is the user actually interacting with?
Yeah, I think I would agree that practically for both the systems to go down at the exact same time is probably nearly impossible, right? I think that, and that's what we are hinging on, and that's what we are kind of basing everything on, actually, if you look at it. And that's the reason why, and also the advantage we get, like Rituraj said, and that's what I wanted to come back to, was that another critical factor in all this is that if the client is demanding that I should not lose data beyond, say, 5 minutes, then you really don't have an option, right? Because if my downtime is an hour or two, right, then, and that you lose the kind of deal with that, then you don't have an option and you have to go with this. So that's why in theory it's both are probably right.
It's an interesting problem, like,
yeah.
because it is all about like, okay, what is your context? Where are you drawing the boundaries?
Yeah.
So it is an interesting question.
Yeah.
Individual component failure का अगर probability higher हो रहा है, then is that better, or keeping that component pristine is better?
Pristine, exactly.
Maybe if we do like a live test, in some cases that will actually perform better. Who knows?
Yeah, I think so. I think the practical answer we've kind of got it on is that if your time to restore is high, I think having a pristine copy is better, right? If I have 2 hours to restore a system or 3 hours to restore a system, what we measured 4. So let's let 4 be the boundary. If I have more than 4, so it depends on the client. If you have more than 4 hours to restore a system, by all means don't create a cluster system, right? Create like an independent system. You don't need to kind of thing. But if your time to restore is say less than an hour also, there is no way you're going to achieve that. And there is human capital involved, you're not going to achieve that. Then you have to go with the cluster system. I think this is the line where practicality and being an engineer trumps being a mathematician, right? So they'll be like
throwing a hat to the mathematicians. Obviously, it is like we understand that over time, if you keep adding boxes, the probability of failure will be definitely much lower.
Yeah,
but as we said earlier also, it's not possible. You can't have any number of boxes, so you have only 2, so you have to make some practical considerations also. But maybe this whole system works when it's 3 or 5 nodes. It's great, but maybe when we run the benchmarks, maybe the 2 system actually doesn't perform as well as the system living in them. But yes, definitely with regards to data backup and data loss, we didn't really have a choice. So
yeah, we don't have a choice, and that's actually been the driving factor actually of this thing.
Yeah, that we don't have that capacity to say to somebody that hey, why don't you take a break for like 4 hours.
so sometimes the right constraints can actually push you to the right decision. So and that's the case here actually.
Yeah.
But
definitely.
Yeah.
I think I'm done with the topics we had at hand. If anybody has any other questions or anything that we want to discuss.
No, I thought it was a pretty concise yet very interesting conversation.
I think it was pretty fruitful. Awesome. Rituraj was part of a podcast for the first time. What was your experience like?
It's very hard, in a way. It's hard actually to speak from a point of view where this is the things that were being discussed, and most of it, fault tolerance as a whole is like mostly out of the developer arena. It's more of the system management or administration or DevOps kind of field. So it's really challenging for me to be a part of this, but I really enjoyed it.
Likewise, thanks everyone.
Awesome. Thank you so much. Like and subscribe, and I'll see you on the next episode or whatever we are discussing. Cool.
And we're not mathematicians, so if maths में कोई गलती होगी, please छोड़ देना. We're engineers with modern mathematicians.
We're trying our best.
Alright, thanks. Bye.
Thank you. Bye. Thank you.